Hello? So does it work? Okay, so it is, I am very pleased to make a talk at this conference. I will talk about two different things in fact. One is the study on different aspects, quantitative aspects of the internet graph, degree and edge distributions. And the second is how these two aspects could be captured, predicted, and estimated by preferential attachment model, random graph model, in comparison with different random graph models. And we conclude that preferential attachment is in fact is a better explanation of the internet graph than some other models. So here is the outline. First, we discuss the quantitative aspects, degree and edge distributions. Then I remind what the Buckley Osthus random graph model is. I describe what is web-host graph in our study. Then I explain how we fit the Buckley Osthus model, its parameter, to the web-host graph. And after all, when we obtain a good results for the Buckley Osthus random graph model to capture the internet graph, I compare these results with those for different random graph models. First of all, we consider two basic aspects of quantitative aspects of graphs. First is distribution of edge of degrees, where this distribution is in fact a function of one variable d, and this function is the number of vertices of this given degree d. It is well known. It is studied. It is well studied. It was shown to follow the power law for many real-world networks. And the second distribution is not well studied. It is not well known. It is a more difficult thing. It is because it has two variables, d1 and d2, and it indicates the number of edges in a graph, whose such that the degrees of its ends are d1 and d2. So it is if the first distribution is about the degrees of vertices, this distribution is about the by degrees of edges. Okay, so in fact, we study not the initial distributions, but the cumulative functions of these distributions, because so the formulas that define these cumulative functions are here. These are integrals of the initial distributions, and these cumulative functions have lesser variation. They are more smooth. They are eventually look like monotonous functions. So it is very convenient to study their regularities instead the regularities of the initial distributions. So in fact, this is a simple thing, and this can be described as the probability or that probability for an edge with maximal degree greater than d1 and minimal degree greater than d2. So it is the probability, the conditional probability that the multi-degree of this H. Okay, so it is the conditional probability that for two vertices of degrees greater than d1 and d2, this pair of vertices are connected with an edge. So what is that function? Okay, and in fact, this function, the edge distribution is in some simpler way were studied as previously as assertivity. It is a well-known aspect of graphs, and it can be derived from the edge distribution by this formula. One can prove it, and so we can, and so we. It is worth mentioning to say that edge distribution is thereby something more informative, because assertivity is a function of one variable, and edge distribution defines assertivity function, and in fact this edge distribution is a function of two variables, so it can be more rich. It can provide more richer information about the graph. So now I remind the definition of the Buckley Osthus implementation of preferential attachment. So Buckley Osthus random graph model is in fact a series of graphs, not one graph. Series H1, H2, and so on for all range of values for n, a natural number. And it is defined as follows. So H1 is just one vertex with a self-loop. Vertex and a self-loop. Then to obtain HT from HT minus 1, we add a new vertex and draw one edge to one of the existing vertices with probabilities that are defined by these formulas. So the probability linearly depends on the degree, on the current degree of degrees of vertices. So I draw an edge, then I draw another vertex, one more edge, and the fourth vertex, and an edge. And this is the definition of the Buckley Osthus graph model for the case where the number of edges equals to the number of vertices. In the case of m equals 1. And generally, if we want to obtain a graph with more edges, we take a graph defined above and just merge vertices as it described here. So, for example, if we want to obtain a graph with two vertices and 4 edges from this graph, that is H4A1. And we can obtain H4, H2, A2 by merging these vertices into one and these two vertices into one. And then we obtain a graph like this. And the second edge, the second vertex has two edges, one such and one such. Okay? So that is the definition of the Buckley Osthus implementation of preferential attachment random graph model. So in fact, there is the following. So the history of preferential attachment that explains why preferential attachment appeared, why it was invented, is the following. First of all, preferential attachment explains the power law for degree distribution. And it was introduced by Barabashi and Albert. And the first precisely defined, mathematically defined model of preferential attachment was done by Balabas and Riordan. But in fact, that model follows power law for its degree distribution with the given exponent 3. And this exponent is unrealistic for the web graph. To this end, Buckley and Osthus generalized the above model by introducing initial attractiveness parameter A, that is here. A is the initial attractiveness parameter, and this initial attractiveness parameter enables to tune the exponent in the power law for degree distribution. And what is our contribution to this history? Our contribution is the following. So in fact, besides the Buckley Osthus random graph model, there are also different, not preferential attachment only, but different random graph models that can as well describe and explain degree distribution. But in fact, we show that for an arbitrary random graph model which describes degree distribution, this model will fail to describe the edge distribution of the web graph. And preferential attachment does describe the edge distribution of the web host graph. Here we start with theoretical results on asymptotic of the quantitative aspects for Buckley Osthus model. So as we said, the degree distribution follows the power law. And the edge distribution can be described by this function. It is more convex because it has three non-trivial factors. These results were obtained in some general form by Grechnikov, and we use these results by applying these results to our cumulative function. So we take these descriptions, we integrate them, and obtain this function that estimate our cumulative degree distribution and the cumulative edge distribution. So I know that, in fact, the second result works in the case when D1 and D2 are significantly different, has significantly different values. For similar D1 and D2, it is not proved theoretically it is not proof that the age distribution follows this law. So I do not provide exact mathematical formulas and definitions because they are very difficult to see on the board, and these are some informal explanation what they mean. So in fact, it is now we talk about the web host graph. What is the web host graph? It is its vertices are web hosts, and edges represent links between web hosts. And the main assumption in our study is that the web host graph follows the Buckley Osthus graph model. It can be considered as a simulation, as an instance of the Buckley Osthus graph model. And in this assumption, in this assumption, we conclude that the degree and the cumulative degree and cumulative age distributions should follow the asymptotics that are theoretically obtained for the Buckley Osthus graph model. And in fact, this assumption also implies that A1 and A2 are equal, because it is the parameter of the same Buckley Osthus graph model which generates the web host graph. But I want to say that only the fact that some graph follows these two laws does not automatically implies that A1 equals A2. So in fact, there are random graph models which follows these two laws, two estimations, but with different A1 and A2. And in fact, for the web host graph, we obtained that A1 equals A2, as I described now. But first, to describe our experiments, I should say something. Huh? Yes?
At least on the first sight, it looks very strange for me, because this is like a joint distribution, right? So if you take some marginal distribution, right, you should get some certain quantity, which can be expressed in A2, right? So what is that model which gives different A1 and A2?
It is, so I will provide example. I was going to provide example further, and I can just say that it is GDC, for example, GDC model, configuration model.
Okay, so if you will talk about this later, so let's not. If you can, maybe you can speak a bit more on this point during your presentation at a later point. Yeah. Yes.
Configuration model is the model for uncorrelated network. It has no any correlations, and degree correlations that trivial.
So in fact, I guess that the age distribution will follow some simple law without of the simpler form of this form. It is like this. Not A. There will be some function of the exponent in the parallel law. In fact, it can be shown theoretically. It is not difficult, but it was not the focus of the talk, so I didn't provide. But maybe it was a mistake. So now I just return to my talk. We use the following data. The base crawled by Yandex, cleaned from spam and duplicates, page duplicates. Vertices are domain owners. It is almost the same as domains, but some domains, in fact, consist of different pieces, different three-level domains that, in fact, belong to different owners. It is big domains. It is for hostings, for hosting providers. And in fact, I should mention that for each two vertices, we draw only one edge between two, only one edge if there was a link between two pages of these owners. So there is some statistic on the number of vertices and number of edges in the obtained web host graph. Next, we fit the Buckley Osthus random graph model to the web host graph. And we can do it by two different ways. We can fit it, we can tune the initial attractiveness parameter derived in the best fit to the cumulative degree distribution, so as the observed degree distribution of the web host graph is close to this function. And the second way is to fit the initial attractiveness parameter in order to obtain the edge distribution similar to this. So we conducted both these procedures and obtained the following results. We obtained very close values of A. Here we provide also mean squared error of prediction functions. So it is a deviation of the predictive functions from the observed. And we also performed some bootstrapping by sampling vertices and by sampling edges. 100-fold bootstrapping, and measured the standard deviation of obtained A's. And here you see the results. So we surprisingly see that the obtained values are very close to each other, and this is the reason to conclude that the same specific Buckley Osthus random graph model with the same value of parameter A can accurately approximate two basic aspects, two different aspects of the web host graph: degree distribution and the edge distribution. And hence, assortativity as well can approximate. But now I provide the figures that capture the real world degree distribution in black and the approximation we obtained in red. Here you see the cumulative edge distribution, real cumulative edge distribution in blue, and approximation, theoretical approximation in green. So in fact, it better works for, as you see, for degrees, for points that are that stay part of the diagonal, and even for the diagonal, the predictive function can approximate the concave around the diagonal. And I can I want to note that this concave would not be possible to predict with a simpler function for the edge distribution like this. But in fact, this model predicts the edge distribution. But is it really surprising? In fact, we can suppose that any random graph model that captures the degree distribution will immediately automatically predict the edge distribution also. Not any random graph model, but maybe if it is reasonable enough, it will predict. And to answer this question, we consider two different random graph models, as I said, GDS and HK. Configuration model and Holmkim model. We chosen two graph models that follow the Powell law degree distribution to show that this model can, even if they accurately capture the degree distribution of the web-host graph, they can fail to describe the edge distribution. We simulated several graph instances for each of these three models, Buckley Osthus, GDS, and HK. We derived degree and edge distributions and compared these distributions with the web host graph and obtained the following figures. On the left, we have the Buckley Osthus simulated. We have in cyan the edge distribution for the Buckley Osthus model. Here in red, we capture the distribution, the edge distribution of the GDS, and here you see the edge distribution of HK. In fact, HK is less interesting for us because we cannot tune even the exponent in the power law for the degree distribution. And the GDS graph that was simulated was chosen in such a way that the number of vertices, the number of edges is the same as in the web host graph, and the exponent in the power law also coincides with the exponent that we obtained for the web host graph. It is minus 2.28. So we see a significant difference, and in fact for GDS you see that the edge distribution is similar to a hyperplane in the log scales, which correspond to that I said that it can be approximated by this function, by a function of this type, of this form. So here in this talk I used the results from the first reference. It is the paper that is published at CIKM last year, and the theoretical results were obtained by Grechnikov, and here you see the name of that paper. So that's all. Thank you.
Questions? Yes, Nelly?
Do you have any explanation why this inferential?
Same information for what?
Yeah, so this, I read this paper already, and it is all surprising that you had initially two parameters, and then it turns out that one is enough, that these two estimations are the same. So what do you have any intuition for this, why this happens?
So I guess that I said that the intuition is that preferential attachment model captures some real world laws, some physical, some laws of the graph, of the growth of internet graph, and it can capture not only these two distributions, but also some other things, I guess. Not all the things. We know that the clustering coefficients, for example, and many different things is not correspond to this, to the preferential attachment model. But the main purpose of this talk is just to say that degree distribution is not the only thing that preferential attachment can capture. There are some also different things that are close to these general distributions and to the degree distribution that can be also captured. So it is just a physician law.
Yeah, but it is not for every graph, because there are many modifications. Preferential attachment, for instance, if you think about how blog discussions develop, then you need more parameters, and there are some other examples. So in this sense, maybe this particular graph is so well described by preferential attachment, which is very interesting.
Okay, yes. Yes, it is indeed the question why this graph, the webhost graph, is follows the preferential attachment model. Yes, and we have no answers yet.
Do you know any other ideas part of power law? Something like geometric distribution, for instance.
About what?
Regarding this degree distribution of degrees. Anything part of power law?
So I guess that one explanation is the GDS I told about, that says that the probability of NH is proportional to the factor of two factors. First is the degree of one vertex, and the second is another. But this explanation is not generative, and it is not good. But in fact, I'm not sure if there are different explanations of the power law distribution.
No, I didn't mean any explanations. Just do you know some other models?
Other models. Which can explain degree distribution. Yeah. No, okay, but what does mean explain? So there are models that there are models that can model the degree distribution, the power law degree distribution, like GDS, like Holmkill, and some others. But the question, what does mean explain the power law? It is not so trivial to
good law, physical law.
Yes? Can you use the microphone?
Sorry. First of all, they call me this model with a mixture of indifferent preference and proportional preference due to Holme, for example, yes? Holme-Kim model. It generates degree distributions with gamma bigger than 3, so that it's strange to compare with anything. Its degree distribution is very different, so that it's not model to compare.
But we have taken the parameters of the whole Kim in order to obtain the model which follows with the degree distribution with the exponent 3. It is the only way. Yeah. Yes, but you are right. Yeah,
You-
it is
you
not.
make-
Yeah.
You make comparison with cumulative this degree distribution, and it looks qualitatively always it's monotonous. The growth from from 0 to 1, yes, and I think a lot of models will fit qualitatively well.
No, the cumulative.
But the problem
Sorry.
is that I
It is
know
not monotonously grows, but it's in fact it decreases like this
I know
because it is cumulative, but it is cumulative from the right hand side. It is cumulative from the right hand side. Yeah, yeah, yeah.
But I know absolutely certain that our model was checked many times, which is actually equivalent to this Osthus. How is the name? The model of
Buckley Osthus, yeah.
It's absolutely identical. It's identical. It's simply we simply introduced the additional initial attractiveness. We even invented this term in 2000. And people checked it, tried to compare just the correlations for different real-world networks, and they saw that just in internet, in the web, some versions of it doesn't describe quantitatively the correlation, the degree correlations. It's a very primitive model. Imagine that you have a recursively growing graph. It's almost a Barabashe model. It's
Yeah,
very
but in
strange
fact,
to have
the Webhouse graph is disassortative. It has negative assortativity. In fact, we obtain the.
There are much more realistic models.
Okay.
Which, for example, a recent model due to Bagunia and Kryukov and some other guys, which is much better, give much better description and generate power laws and generate clustering and all this stuff. So it's too simple model to believe it. That's what I think it's very strange. No, it's very strong claim. You made a very strong claim that so simple model it produces realistic correlations.
So the main,
How?
in fact, the main claim of ours is that preferential attachment is a better explanation than non-generative graph models. And do you speak about generative graph models or not?
I speak about model recursively growing models under the mechanism of under the preferential attachment mechanism.
Okay. Okay, but if, in fact, yeah, yes, I see.
Other questions or criticism or okay?
Just to look on this picture, you can see that there are some outliers here, right? Or I'm wrong?
Okay, yeah.
So, and your model doesn't fit outliers perfect. So this is, I think, it's comment similar to yours, or not?
Anybody else? Or should we perhaps then wrap up the section and thank the speaker again?